Welcome to Depth Camera Central Volume 28. This is Z2 Part 2. In the first part, I discussed motion sensors, accelerometer and gyroscope, position sensors, barometer and magnetometer. From 25 Hertz up to 400 Hertz, we talked about the pose update rate up to 100 Hertz and the pose drift translation 0.35% and rotation 0.005 without loop correction. We also discussed different technologies for 6 degrees of freedom, visual inertial stereo, also SLAM, simultaneous localization and mapping with advanced sensor fusion and thermal compensation. And this new sensor has a 120 degree field of view for the Z2, 110 degree on the horizontal, 70 degree on the vertical, and again the depth range in the non-ultra mode is 0.2 to 20 meters or about 0.65 to 65 feet. Now this is the first stereo camera to integrate an AI inference model or a natural stereo depth sensing based on a 7-layer perceptron, or a machine learning model is training itself. But today I want to talk about object detection in 2D and 3D. So persons, vehicles, different detection outputs, bounding boxes, 2D and 3D, which is what you can actually see here. It's really nice. I love it. And the detection range is 0 to 20 meters for 3D bounding boxes and up to 40 meters on 2D. And you can have all kinds of different integrators on the outputs for location, speed, unique ID, and different segmentation masks. But also we're going to go into skeletal tracking, 18-point key points, and head bounding boxes, and you can do this up to 10 points. But look at how you can actually track some of this. And I always come back to robotics. We're building, the Musher platform at the University of Washington. We did that race last year, and it was really amazing. But you can integrate this, and again, the system needs to support CUDA processing up to 10. This is on CUDA 11.0, running around 3,000 CUDA cores. But you can do a lot of different kinds of tracking. Again, but look at the bounding boxes, and you also will have the different distance here. You can see in the just above me on this side right there, you can actually see how far away I am from the camera, and then this image behind me is a bird's eye view, which is really nice. But as you actually track in and out of this, what you can actually do for the system, and it should change the different colors there. So now you can actually track around a different part of the image in different colors, and you can do up to 50 different people. With this right now, I'm testing up to 100 in the AI inference model, and that is just fantastic. If you're talking about robotic applications, emerging technologies, transformative paradigms, all of this stuff is here. And I talk about the acceleration of different technologies, especially in the last 12 months, with all these things going on in the world, it's accelerated up to 12 years. It's truly remarkable. But now we need to jump on these different types of technologies and start integrating them in all facets of our civilization. And that's why I want to continue showcasing this to everyone out there freely, so you can come to this channel and learn as much as you can. I've received a lot of questions in regards to Unity integrations and ROS and MATLAB. I may create a third volume for Z2 just to discuss a lot of these different integrators, because it's very comprehensive in how you have to set it up and then bring everything into the packages and program in C++ or whatever your preferred programming languages are, okay? But this particular algorithm, I've been testing a lot in ROS, the robotic platform, and it's really, really easy to integrate. I've been using an NVIDIA Jetson AGX NX series, and it's exceptional. It's a very powerful platform. But I also wanted to showcase to you guys the body tracking algorithm, so you can see what that looks like in the AI inference model and compare it to the Microsoft Azure Connect or many of the other different types of body tracking, OpenCV. I've done many different videos on body tracking, skeletal tracking. This has 18 points for key points for body tracking. And let's go ahead and take a look at how accurate that is. And I will also do some positional tracking so you can see what that looks like. And I'll jump into showing you the sensors for the barometer, the accelerometer, the gyroscope, so you can get a clearer picture of what that looks like and how you can use it. And in the future, they're also having they're integrating a cloud monitoring service, so you can have up to 20 different cameras located at different facilities, and then you can bring them all up and body track and count people and have a logistics and different types of applications. It's truly incredible. Let's go into body tracking for the 18-point key points right now. Let's go. Hello, welcome back. So what you're looking at here is skeletal tracking at 18 body key points. And again, it's using an AI inference model. So this is not a vertical cavity surface emitting laser. It's not sending out a time of flight signal. It's not using light imaging detection and ranging like the new Apple iPad or different types of phones. This is just essentially just like your eyes or a Tesla where it has 8 pairs of stereoscopic cameras, right? So it's just using the triangulation from one angle to the other, binocular disparity, and inferring depth out to up to 40 meters. That's sensational. I love this camera system. So again, the resolution on this thing though has around, I think it's 2 micron for pixels, and it has 2 4 megapixel camera sensors, and then it has for the lens type, and it has a wide angle 8 element all glass dual lens with optically corrected distortion. It's really amazing, and at low light, I want to show you what this looks like with at lower light scenarios. So let's go ahead and take a peek here what this actually looks like. So again, this is very low light. I don't have a sensor in here, but you can look at that and it is not negatively impacted like you think it would be. Some of the other systems I use and test are extremely impacted when you lower the light level. And I've always talked about this, where the advantage of using an active stereo system sending out infrared at night when you can't actually see things, right? So if you move one way or the other in low light scenarios, it would drop out the body tracking for the 18 point or 20 point. Even if you're using an inference model, it wasn't able to actually capture enough light coming into the system. This does not have a problem with that. This new sensor is 40% more sensitive than the Z1 and almost every other system that I've tested on the market, which is it's exceptional when you compare it to every other competitor in the market, right? And then you talk about the resolution and the 120-degree field of view and that native 16 by 9 format. And I believe it also has an electronic synchronized rolling shutter, which helps with image quality as well. So there's a lot of different things about this camera that I love, and these new integrations, also cloud remote viewing, which I talked about previously, is going to bring more people into the fray to utilize this, especially in robotics and perception engines and simultaneous localization and mapping, so robots know where they are in the environment and in the world, okay? So I think next we're going to look at the positional tracking system. I've showed you this previously just on a very small $120 camera, but now I want to show you what it looks like here as I track all the way around, and then we'll go into the barometer, accelerometer, magnetometer, and all these other different sensors so you can see what that looks like, okay? Let's jump in. Let's jump into positional tracking. So what you can see here is the translation in the upper left-hand corner and the rotation in radians. So we use this quite a bit in robotic systems when we're going around to track. And why is this an important integrator when we're looking at feedback mechanisms? Because we have to understand the pose of the robot, and then where the robot is, there's always some kind of an error or deviation rate. And we can feed these mechanisms back into an Ackermann control system, essentially telling the motors or the drive systems to make certain corrections when it's going around. If you're doing drifts, I saw this on an MIT robotic vehicle last year, and that's the part that can really transform your robot into an intelligent machine. So using these systems, going around and around and around thousands of different times, this is how you train an AI inference model, right? And that's the validation and the improvements are nearly automatic. And you have to use this if you're in a competition for any kind of robotic platform, whether it be fast race cars or something out in the field, like stuff that DARPA was using many years ago. This is the integrator that you should be using. It's very simple. There's a sample script here in Python and C++, and within the new SDK that I highly recommend you guys go ahead and use. Let's jump into the next portion of this. Let's go ahead and jump in right now. Welcome to the sensor viewer of the Stereolabs Zed. This is the accelerometer, the yaw, pitch, and the roll, the XYZ. And the thing I really love about this, from a engineering and scientific perspective, is that you can record this out to a file. So if you have this on a robot, if you have this on a drone, an aerial platform, a scientific platform, you can capture all of these different impacts and you can trend them analytically, and you can feed it back into the system. I think every type of bit of information and data can always be fed back into the system to retrain it and improve it, to enhance efficiencies, to improve return on investment, improve productivity. All of these things are part of the robotic platform, part of the intelligence that you're going to embed, and you want to make it automatic, and you use AI inference models, machine learning models to accomplish those tasks, right? But look how quick this is. This is around 400 hertz on that, and you can see how quick this thing moves. And what I want to do is show you the different types of applications from the accelerometer, the gyroscope, but also show you the temperature. Again, is in C. I think for the conversion from C to Fahrenheit, 1 times 1.8 plus 32. But now we're going to come on to the gyroscope, and I want to show you what this actually looks like here. It's really, really cool. But again, the same kind of information, very, very quick. You can look at this on a timeline of 10 seconds, and you can see how fast this is. We haven't had this kind of information, at least this seamless kinds of access to the sensor streams on these types of cameras, and it's really extraordinary. I think it's going to help many different interested people and new types of students and scientists implement and design these into their applications and to their platforms more seamlessly than we've had in the past. I think that's always been a struggle when we're looking at these types of sensors, is trying to make things easy to implement, right? And that's the challenge, is having an agnostic cross-platform type solution that anybody can use and throw into their project really quick with an SDK that doesn't matter what it is, ROS, MATLAB, Python, OpenCV, you just want to grab something and drop it in and have it work. And that's what this does, and Stereolabs really deserves quite a bit of credit for developing this as well as they have. What you're seeing here, this is the barometer, and here's the magnetometer. Again, this is looking at the magnetic field, and again, here's the temperature. So you can see the advantageous and the usefulness of this type of sensor when you're developing a robotic platform. When you have a drone, you're going to see these all over the world in just a few years. And I would say it's probably going to be this year in 2021, might be in 2022. We'll see where this year goes. But again, these kinds of sensors are going to be ubiquitous across the entire industry. Spatial computing, emerging technologies, all those inflection points are all meeting at the same time. It's really exciting. I love it. I love creating these videos, and I love helping you guys understand it, and then you in turn help me understand things I didn't see. That's really the advantage of this new world, all these information sharing capabilities out there. But thank you so much for tuning in to Volume 28. I may sneak in Unity at the end of this. If I don't have time, I'll create a Part 3 for the Z2 that includes just some discussions on the robotic operating system, OpenCV, OpenGL, also MATLAB, different kinds of integrators. Again, Unity, if you want to use this in a Unity project. I did forget about you. I remember you're asking questions on YouTube. I do not forget. So thank you very much for tuning in to this channel. Please subscribe below. If you have any questions, let me know. I'm always here. I love fielding questions. I love interacting with engineers, students, professors, anybody out there who loves this technology as much as I do. So thank you so much. I hope you have a wonderful weekend. Okay, I know I said this was the end of the video, but I had a little surprise for you, and I forgot to include the vertical and horizontal plane orientation for the Stereolabs Z2. So what you're seeing here is the horizontal plane detection, and you can do the same thing here right on the wall, and we can do the same thing right up there on the ceiling. And blue is unknown, so it doesn't know that, right? So we can kind of click down, and you kind of just press P and map all the way around. Now this is very advantageous in stereo mixed reality pass-through, like for the Z Mini. If you're implementing like a Vive or a Valve Index, and you want to have a higher quality mixed reality experience, you could use something like this so you understand the plane detection, very similar to the mixed reality toolkit, where you're looking at walls, edges, detections, and ceilings. And so you can place holographic content there, but also for robotic platforms, so understands in reference to its pose orientation and translation, you can calculate some deviation errors, and you can do this like a G mapping index in ROS. So very, very useful. Again, I've been doing a lot of the testing on this. It's very helpful in all different types of emerging technologies, but more specifically in drone technology, in robotic platforms, autonomous platforms, and again, in spatial computing and mixed reality stereo pass-through. Hope you enjoyed this. Thank you so much for tuning in to Depth Camera Central Volume 28. Please subscribe today. Have a great day. Bye-bye.